Okay. Okay, so let's start. So in the last lecture, we were looking at automata with outputs, right? So we looked at Moore machines and Milli machines. So what was a Moore machine? So uh, what was a Moore machine? So essentially, you had output on the states. And what about Milli machine? You had output on the transitions, right? So and then what else did we say? Uh, hmm, oh, no, it shows right now. Uh, that, okay. So and what are milli machines? So milli machines are those machines which have output on the transitions, right? And then what else did we say? We say that the Moore machines and the milli machines, they are equivalent. But there was some small technical issue there, right? When you were translating, what was that? Input length was one more. Okay. So one, not input length, it was the output length. Output length was one more than the length of the input in the case of Moore machines, whereas for milli machines, it's equal, right? And then we say that you can translate Moore machine to milli machine. And how do you do that? How did you translate Moore machines to milli machines? Uh, right. So if there is an output on the edge, which is an incoming edge, if there is an output on the, sorry, if there is an output on a particular, so we are talking about translating from Moore to milli machine, right? So if there is an output on a particular state, then on the incoming transition, you put that same on all the incoming transitions for that particular state. So essentially what are we saying here, like if you consider this, so if you have an output here, let's say some output B, and this is a Moore machine, and then in the corresponding milli machine, what we would have is like, so on all the incoming transitions, right? On all the incoming transitions, you would have an output B, right? So this is what we saw, correct? And so we did this thing. So if you have, for example, lambda is the output function for the Moore machine. And then we are talking about how do you get the output function for the milli machine on the transitions, right? So this delta was the output alphabet, and here it's the lambda is a function from the state to the alphabet for Moore machine. For milli machine, it's a function from the transition to the output, right? And what is lambda prime? Lambda prime of q prime a, which is your the edge, right? The transition. It is essentially um, um, so I think there should be. So if you have an edge from q on a, there is an edge equals to q prime, correct? So we are so and suppose there was this b here, then it is the lambda of q prime, which you are the lambda of q prime is you are making this the same as lambda of so lambda prime of, okay, so I think we made it like this, sorry. It was here and it was So lambda prime of q prime comma a, is this okay? Equal to lambda of delta of q prime comma a. So it was correct only. So, okay. And so suppose this is, so this should be q. Okay. So what we are saying, so if you have this here, if you have a b, then you would like to put it on the transition. Clear? Okay. So you have this lambda, which is an output on the state, and we are talking about constructing the lambda prime, which is on the transition in the case of Mealy machine. And as we saw, that if the output on a particular state is suppose B, we are going to, in the case of the Mealy machine, we are going to put this on the transition here, right? So, and you have Q prime, here you have Q, and so this is the Mealy machine, right? And right. Okay. Okay. So I think this is fine. Okay. Now we also talked about the other direction. So how do you do that? So how do you do that? Right. So what is the question? So we are now given a Mealy machine. We are now given a Mealy machine, let's say M, right? Q sigma, then you have the delta, which is the output alphabet, delta. And then there is a Q0, we also have a lambda here, right? Okay. And maybe let's say I have delta 1, lambda 1, Q0, and we want to construct a mood machine. Q2, okay, so it may be Q0 prime, or let's say this is Q0 1, here I call it Q02. Correct? So in the Mealy machine, what happens is like you have the outputs on the transitions. And now in the mood machine, you'd like to have the outputs which are on the states. Correct? Now it can happen, suppose you have something like this, and there is something like this, and you have an output, let's say, your output, suppose the input is here A, the output is of the form, let's say it's a B1, and you have an input D, the output is B1. Here you may have an input C, the output may be B2, and so on. Correct? And the thing is, like, you cannot just put here the output to be just B1, right? You need to have, like, so in the case of mood machine, as you see, you would need to have states here. One state will have an output of B1, the other state will have an output of B2, and so on. Correct? So with this intuition, how do you do that? Like, so let's say I have, this is Q1, this is Q2, etc., etc. So how, so what should be my Q2 here? What should be my capital Q2 here? Q1 cross delta, right? Very good. So we can have, sorry, so we can have our Q2 to be equal to Q1 cross delta, right? So here, for example, then we have a state which is Q2, we have a state which is Q2, and then here, let's say we have Q1, you read A, you go to Q2, comma, this kind of a state, Q2, comma, B1. Here, you go to a state, which is Q2, Q2, comma, B2, and so on, right? So you have this state here, right? And then on C, you go to this Q2, comma, B2. Clear? Okay. So now, how are you going to define and Q0 to the initial state can be something like it can be some Q01, comma, some B, or some B belonging to delta. So you can just choose your initial, whatever is the output for constructing the moon machine, right? And now, how are you going to define the delta 2 and the lambda 2? How are you going to define it formally? If I have to talk about the delta 2, how are you going to do it? Okay, so let's say delta 1 of Q1, comma, let's say B1, and then on A, you would go to Q2, comma, B2, if what? If what? If delta 1 of Q1, comma, A, you go to Q2, no, so we are talking, yeah, and lambda 1 of Q1A equal to B2, right? Okay. Right? Okay. So you are going to define it in this way. Okay. And lambda 2, you are going to define it in like Q, comma, B equal to B. Correct? So we have defined the Moore machine, the translation from Moore machine to Moore machine. Right? So this kind of translation is not very difficult, but you should be able to do it yourself. I mean, you need to put some time within the lectures so that like you get more used to it. If you're not doing that, then yeah, I mean, I think it's good that you are attending the lectures, but I think you need to be a bit more familiar also. Okay, right. So then what did we say? We said that for every millimachine, there is so essentially this shows that so I can write a theorem which will say for every millimachine, there is an equivalent Moore machine, okay, such that, okay, here I would say the output of the initial state of the Moore machine can be ignored. So this is just a technical thing, right? This is just a technical thing. The first output of the initial state you can just ignore. So modulo that, they are equivalent. Right? So what you could try is something like the following, that something like the following. So we looked at, for example, milli machine, right? So we looked at a milli machine for 2's complement, correct? So can you construct a mood machine for 2's complement? So we did this in last lecture. Construct a mood machine for 2's complement, right? Okay, so this is something you should try out again as a homework assignment. I mean, these things you should try to do yourself. I mean, only then you will be able to be a bit familiar. It's not difficult. It's not very difficult, but unless you do it, you won't be able to kind of be familiar with this small tricks or techniques or whatever, right? Okay. So there were some other things that we discussed during the last lecture, like, right? For example, the finite power property. What did you find? Did you, for example, do you think there exists an algorithm to check the finite power property? So what is, sorry, you don't know. Okay. Uh, okay. So what we'll do is like, we'll put it on Akadli, that we'll start a discussion thread there, and you can, so I'll put some links and then you can tell me like what you found there. Okay. What else did we discuss apart from this algorithm for the finite power property? There were some other things. Sorry. Did you find? What is that? Extended star height. So what was the problem? Yeah. So can you think of a language that has extended star height 1? So did you try it? No? Okay. So do you want to try it? I mean, spend some time, just do some searches and try to figure out. I mean, you can also think of yourself, but these things are going to be useful. Okay, these things are going to be useful. So what are the things that we discussed during the last lecture? So one was algorithm for finding FPP, finite power property, and example of regular languages with extended star height 1. With extended star height 1, right? So these are things. And was there anything else? Yeah. So what was the language? Could you epsilon? Huh? Union A square A star. Okay. So okay, I can just write maybe epsilon plus. So what is the order, right? Order of the language, right? Again, I don't want you to prove anything, but you should argue that, okay, this is what the order should be. 3. Okay, good. So I think this is indeed 3. And can you tell me why it is the case? So everything that you take from one of the, yeah. So for example, if you take, let's say A6, right? Yeah. So if you look at, for example, so this is the language, right? So this is R if you consider LR. So L, and suppose I call it L. Okay. So then A6 is not in L, correct? And then A6 belongs to L of 2. A6 does not belong to L of 2. A6 belongs to L of 3. So this gives you an intuition. And then everything that you look at, for example, A7, A8, everything that you look at, they will belong to L4 and L5 and so on, right? I mean, everything also belongs to L3. Okay, so if you look at A7, A8, everything belongs to L3. So what was your argument now? The number of A's will be 2 mod 3. So the number of A's, so let me call it hash A in W. So this is how I represent the number of A's in W in a word. So what you were saying, it is 2 mod 3. And why is this 2 mod 3 important? Because it is A to A star. A to A star. Yeah, A to then 3A star. Okay. Right? Yeah. And so how can you get, for example, 1 mod 3? You can get just 2 of them, right? So you can get 2 such things. You can get 2 such things and you can get 1 mod 3. And how can you get 0 mod 3? So taking 3 of them, taking 3 such thing, and then you can get this thing, right? So indeed, like, yeah, once you observe that this particular thing, A6, for example, where do you find it? And then it is there in L of 3, then you can see that the order is indeed 3 for this language, right? So for the other two, let's start. I mean, I'll possibly put something in the on Acadly, and then we can keep the discussion maybe going. But you can also search a bit, like what you think is the case. Okay, so today we are going to start with the, so any question with the milli machine and the Moore machines? No? Okay. So now today we are going to start with the some other closure properties. Okay. So what we have seen so far is closure under union, intersection, and complementation. So how did we see union, closure under union for regular languages? You can consider the DFA and take a product of the DFS, and then sure. So you have, for example, your set of final states. If the constituent DFA have state of states F1 and F2, then you will have F1 cross F2, right? Sorry, you will have, and the set of states are, let's say, Q1 and Q2 with set of final states F1 and F2. Then for the union, we saw that it is Q1 cross F2 union F1 cross Q2, right? So this is for union, correct? So this is your set of final states in the const. What about intersection? What did we do? Huh? It's F1 cross F2, right? This is intersection. You have the DFA, correct? And the set of states in the constructed DFA in the product automaton. So this is product automaton. It's Q1 cross Q2, and the set of final states is F1 cross F2. So these are things that we saw in detail. What about complementation? You just flip the accepting and non-accepting steps. And then we also looked at concatenation and clean star. How did we do that? By looking at the epsilon NFS, right? So these were by product construction. These were by clean star. These were by, we looked at epsilon NFA. Okay, so today we are going to look at homomorphism, inverse homomorphism. That regular languages are closed under homomorphism and inverse homomorphism, as well as we are also going to look at something called quotient. We'll look at maybe right quotient, maybe, and yeah, and we might look at reversal, which is also easy. Okay, right. So let's start with homomorphism. Okay, so let's define what is homomorphism, right? So you can think of like it's a homomorphism. So we are going to talk about particularly monoid homomorphism. We are going to talk about monoid homomorphism. So you recall that the set of strings under the concatenation operation, the set of strings under concatenation operation, so essentially sigma star, it forms a monoid, right? It forms a monoid. So what were the properties of monoid? It's closure, then associative, and there exists an identity element, right? So in this case, we are representing the identity with epsilon, right? So a homomorphism, what is a homomorphism? It's a map from map H from sigma star to, let's say, some gamma star, where sigma is an alphabet and gamma is another alphabet, such that for all x, y belonging to sigma star, we have that h of x, y equal to hx dot hy. Okay, so we are talking about strings. Okay, so this is also like set of strings. This is also set of strings. So what is, and my sigma and gamma, these are alphabets. So this sigma is an alphabet. Let's say, for example, it can be AB. So gamma is also an alphabet. Something like, maybe as an example, you can think of this is 0, 1, right? And given this, okay, and for both of them, the identity element is epsilon, right? It's a set of strings, and so the identity element is epsilon. Now, given this, can you prove that indeed h of epsilon is also epsilon? So this is the property of any homomorphism. We should have that. But what I'm saying is that with this, in this particular case, you can also prove this. In general, you can have, whenever you are talking about two monoids, right? Suppose you have a monoid M1, you have a monoid M2, right? And you can have maybe the identity element can be epsilon 1 and epsilon 2. Okay, if this is the case, then in general, I would say, and suppose there is this thing, a homomorphism from M1 to M2, then you will have H of epsilon 1 equal to epsilon 2. But in this particular case, we are saying, since we are talking about sets of strings, both the monoids, they are sets of strings, you have, so we assume that this identity element is epsilon in both cases. So what was epsilon? It's an empty string. And we are saying that indeed, given this, you can derive this. So xy is nothing but x dot y. Okay. And given this, you can derive this. So how do you do that? Sorry. Okay. So you are saying h of a dot epsilon equal to h of a dot h of epsilon. But how? I mean, how do you say that this is going to be epsilon? This is under the assumption. Sorry, in the left. Okay, so this is h of a equal to h of a dot h of epsilon, right? Hence, what h of epsilon equal to epsilon? Okay, good. Okay, yeah, sure. This is fine. Okay, so now we are going to define the homomorphism for a particular set. So suppose A is a subset of sigma star. Okay, so what is H of A? How would you define this? So here, see, like we have actually, so we are extending this to sets. Here it's like you are having the mapping from a string here, string in sigma star to a string in here, and then here we are extending it to for a set to a set. So how are you going to do that? It's equal to h of x such that x belongs to A, and this is a subset of gamma star. Here, h of A is a subset of gamma star, right? And so this is, and for B, which is a subset of gamma star, we are defining H inverse of B. So this is the inverse homomorphism. What is H inverse of B? What is H inverse of B? Okay, so this is the set of X, right, belonging to sigma star such that H of X belongs to B. Very good. Okay, so this is, we will also call it pre-image of B under H, right? So now to prove the closure, so let's write this theorem, which is closure under homomorphism. What does it say? Let H sigma star to gamma star be a homomorphism. Then if A, which is a subset of sigma star, is regular, then H of A is also regular. How would you prove this? How would you prove this? There can be several ways to prove it. So any thoughts? So what is the most immediate thing that comes to your mind? Okay, so well, I mean, there can be, as I was saying, there can be several things one could do. So let's say, how about you have an A here? Okay, so you just consider the mapping from sigma to gamma star, right? You can do that, correct? Just the mapping from sigma to gamma star, not the whole of this thing. So suppose A goes to, suppose your sigma equal to A comma B, and let's say your gamma is 0 comma 1, right? And suppose A goes to 0 1, right? Now what I claim is that here, when so I have so suppose corresponding to set A, since this is regular, I can construct a DFA here, right? Which accepts, so DFA, let's say D of A, such that L of D of A is A. This I can do because this is regular. Now, what you can do, suppose there is a mapping here, which is A, right? So again, on this side, you have A. And so here, for H of A, what I do, I put 0 and 1 here, right? I'm constructing another finite state automaton. So here, if I have A, I do 0, 1. Okay. Now the question is that suppose if I do this, what am I going to get here? So this finite state automaton, what is it? Is it a DFA or an NFA or what? Is it a DFA? So what transitions are you going to have from this intermediate states? Suppose you have another B here. And suppose corresponding to B goes to 1, 1. So what would you have? You have a 1 here, and you can have a 1 here, something like this. Sorry? I don't understand. From B? No, so the homomorphism, I said it's defined like this. It's A, from A you go to Z, A maps to 0, 1, B maps to 1, 1, right? So you have B, and then I'm on this side, I'm constructing another finite state automaton such that if you are, so this is simulating this. So this one, 0, 1 simulates the A here. The 1, 1 simulates the B here, right? So what kind of finite state automaton are you getting here? Is it a DFA? It's an NFA? Okay. But now suppose instead of B going to 1, 1, could you also have, let's say, B goes to epsilon? It could have been possible, right? I mean, no one prevents you from having that. You could have epsilon, of course, has to go to epsilon because that is the definition of homomorphism. But you could also have a mapping from B to epsilon, right? In which case you will have an epsilon. So the structure that you are getting here is an epsilon NFA, right? The structure that you are getting here is an epsilon NFA. Now, all you need to prove after this, right? So, and then you also have to define the set of final states, right? And I think that you can do. So for example, here, if on a particular transition, you are going to a final state here, then you will say after doing this, I will go to a final state here, right? So this you can do. And then what you would have to prove is indeed this epsilon NFA, right? This epsilon NFA accepts h of a. Okay, prove that the constructed epsilon NFA accepts h of a. Right? And how do you prove that? Using induction. Using induction, right? You would using induction. So which I believe again you can do using, so you would have to define a delta star and a delta prime star, and then you'll say, oh, if I go from, there is a run from here to, from one state to another, then how you can simulate it in the epsilon NFA, and if the run is accepting, then here also you will get an accepting run. Correct? So this is one way to show that. Is it okay? You would indeed have to, but again, I mean, these are things like this construction should now come to you automatically, right? Because we have seen several of them, of these kind of things, right? It should come to you automatically. Now, but there can be other things also, which may be slightly, I'm just showing you because you again need to be familiar with the different techniques. So the other thing you can also think of, like if A is a regular set, then I can also think of using regular expressions. So suppose there is a regular expression R, such that L of R, another technique, right? Another way of proving the same thing, closure under. But it's good to sort of know about these things because you kind of get familiar with all this. So suppose there is a regular expression R, LR equal to A. This is what I'm saying. So now what you can do? What can you do now? You can have another regular expression, right? Such that you do exactly the same thing as we discussed here, as we talked about. So for example, you just think about this part, right? And you apply this mapping on R. You apply exactly this mapping on R. And suppose the resultant, I call it H of R, let's say I call it R prime, right? And then what do we need to prove? That indeed L of R prime equal to H of A, right? How do you prove this? Let's try to look at one or two examples. So how do you prove this? Let's try to prove this maybe. So, right? So this is proof using regular expression. I didn't get into the detail of the previous proof because we have seen similar things several times. I think now it's time that you should be able to work these things yourself, work out these things yourself. So proof using regular expression. Right. So how do you prove something like this? So what is the basic technique? Also induction. And this induction, as we saw, because this is kind of a structure, it's a tree, right? Regular expression can be seen as a tree. So we are going to use structural induction. So what is the base case? What is the base case? So suppose R equal to just a letter A, then A equal to L of R, which is just this thing, correct? So now what is H of A? So what are we trying to prove? We are trying to prove that H of A is L of H of R, right? So this is what we are trying to prove, right? So what is this? So in this case, H of A is equal to H of A, and then what? Is it okay? So H of this thing, this set, you can just apply the H of A and then take this set. So this is L of H of A, right? which is of course the same as L of H of R, because R is the same as this, R equal to A, right? This is what we started with, right? Yes, essentially we are calling it R prime, L of R prime. Clear? What else? I mean, you can also similarly do it for the other base cases, say, let's say R equal to epsilon and R equal to, okay? Similarly, you can, similar as above. Okay, again, you can do this. Okay, so what we can show for this thing that indeed H of A equal to L of R prime, right? Okay, now let's say we look at an inductive case. So we look at an inductive case. You should tell me. So suppose an inductive case is R equal to R1 plus R2, right? And how are you going to do this? Suppose R equal to R1 plus R2. And then we are going to show that indeed H of L of R equal to L of H of R prime, L of H of R. Okay, which we are also calling it as L of R prime. So R prime is nothing but H of R, right? So this is what we need to prove. So we have to prove. Correct. So how are you going to prove this? So let's start. H of L of R. So what is our R? R is R1 plus R2. H of L of R1 plus R2. Then what? Sorry? H of R, what is your question? I don't understand, sorry, cannot hear you. Yeah, so this is what? H of, can you prove this? It's not very difficult to see. So this step. So H of L of R1 plus R2, right? It's R1 plus R2. So what does R1 plus? The plus essentially denotes the union of the sets, right? The language. So first of all, let's look at this part. The language of R1 plus R2, right? It's essentially the language of R1 union. So I think this is, it's a bit of a this thing, but let's say we do this. I mean, it's a, right? So you have this. Okay. So you have the language of, so look at this part, the language of R1 plus R2 is the same as language of R1 union language of R2. Clear? Right? So this is just a simple property of, like you can talk about, like it's a property of regular expression. It comes from the definition of regular expression, essentially. Then what? Then what? So can you say, can you put, right, H of L R1, right, union. So you are taking the union of the two languages, you are putting, you are adding the H, and now I'm saying this is like L of R2. So you have the language, and then you add the homomorphism on each of the constituent languages. Right? Now what? Now what? But Is it very easy to see, or you want to formally prove this? Can you formally prove this? Like, it's not very difficult, but again, like, you can formally prove this. Right? So let's try to, maybe let's just work out once this part. Okay. So let's say H of L of R1 union of L of R2. Okay, H of this thing. So what is this? It's equal to H of W, such that W belongs to L of R1, or W belongs to L of R2. Clear? Now what? This is equal to H of W such that W belongs to L of R1 union H of W such that W belongs to L of R2. Right? Which is equal to H of L of R1 union H of L of R2. Clear? So this is there. Now what? I think this is next step is important. Next what? So this is the same as R1 prime by induction hypothesis plus. Okay, so I can say so this is by IH, induction hypothesis. Right? So what are we going to prove? So we are going to prove that H of L of R is the same as L of R prime, right? H of L of R is the same as L of R prime. Now, what we so H of L of R is L of R prime is what we are going to prove here, right? So to prove H of L of R is L of R prime, correct? So this is what we are going to prove. H of R is the same as R prime, right? So by induction, R equal to R1 plus R2, and we are doing a structural induction. So hence we have H of L of R1 is L of R1 prime. H of L of R1 is same as L of R1. You have this. Now what? Sorry? This is L of R1 prime plus R2 prime. Correct? Now, again, this is by property of regular expression. So this one you get by property of regular expression. Then what else? So L of homomorphism. So this is what is this? L of H of R1 plus H of R2, right? So it is the plus. And it is the same as L of, so this thing inside is the same as H of R1 plus R2, right? So H of R1 plus H of R2 is the same as H of R1 plus R2, right? So this is L of R prime, right? And what was L of R prime? It is H of A. Right? So this is what we essentially proved, like H of A. We started with this. We actually started with this H of A. And then we show that H of A is the same as, which is right? This is the inductive case. And similarly, can you also do for R equal to R1 dot R2, right? It will be very similar. It's just exactly the same. So maybe we can try that also, right? So let's say inductive case. Now you have to tell me the steps. Inductive case, it will be very similar. Just you have to, let's do that. R equal to R1 dot R2. What is R? So we are talking about right? So you have a regular expression R corresponding to A. So A equal to L of R, right? So which is equal to, and what we are going to prove is that to prove, what are we going to prove? H of A equal to L of R prime, right? Because, so what is the idea of the proof? The idea of the proof is that you start from a, so given an A, we are trying to prove that this is closed under homomorphism. So let's look at the broad idea. This, we are going to prove that this is closed under homomorphism, right? This is the whole idea. Now, how are we going to prove it? So we say that since A is regular, there exists a regular expression R such that A equal to L of R, right? So this is, we have seen, corresponding to every regular set, you can have a regular expression. This we have already seen when we studied regular expression. And now what we are saying is that, suppose if you consider, now consider H of L of R. Consider H of L of R. Now clearly, this is also a regular expression, also a regular expression, right? And hence, corresponding to this, thus corresponding to H of, sorry, so consider H of R. Consider H of R. This is also a regular expression. Now corresponding to H of R, there is a language, right, which is L of H of R, right? And we are also calling it R prime. It's the same. It's which is the same as L of R prime, right? There is a language. Now all we need to prove that H of A equal to L of R prime, right? And why this suffices? Because we know that the language corresponding to regular expression is actually a regular language, right? This is a regular language. If they are the same, then essentially we show that the regular languages are closed under homomorphism. Correct? So by doing this, you essentially get a regular set. Hence, this is closed under homomorphism. Regular languages are closed under homomorphism. So this is the broad idea. Now we are proving this thing. We are proving this thing, and we are proving by structural induction on this regular expression of R. So we already showed for the inductive case of R1 plus R2, and now we are trying to prove this for the inductive case of R1 dot R2, right? So how are we going to do this? So can you tell me quickly? So H of, so the broad structure of the proof structure is clear, right? And so H of L of R equal to H of L of R1 dot R2. Now what? Equal to h of L of R1 dot L of R2, right? And we defined such a thing, like how do you define the concatenation of two regular sets? We also defined this operation, right? It's a concatenation on the sets. Okay. Now what? Right? So this you can do. And for this, you would need something of this kind to formally prove this for this step, right? So this needs a short proof, but which is easy. We have seen this earlier, similar things. And now what? This is equal to, this is equal to what? Now what? H of L of R1. Homomorphism on the language of this regular expression, which are on the in the subtree. This is by induction, right? So this is by induction. You have L of R1 prime dot L of R2 prime, right? So this is the important step by induction hypothesis, right? And now again, you can use the property of the regex, which gives you L of R1 dot this, right? And now, right? So this is by property of regular expression. Now what? Next. So this was, if you recall, R1 prime was essentially this is dot H of R2, right? So this is how you are doing this. And by the property of the homomorphism, this is H of R1 dot R2, right? Right? So you are applying the homomorphism on the components concatenating. It's same as you are putting the R1 dot R2 together and then applying the homomorphism. Yeah, we did it for plus also, right? It's this step, H of R1 plus H of R2, the same as H of R1 plus R2. We are exactly doing it. So similar steps, H of R1 dot H of R2, the same as H of R1 dot R2. Right? You just consider two regular expressions, right? So you are applying the homomorphism on one, then taking the dot and then doing this, right? It's exactly, so you have two regular expression dot this. What we are saying now, you take the concatenation, put the H, right? And now, so this is the same as equal to what? L of H of R, right? We are done, right? So it's exactly the same step as the previous one. Now, the one that I will not do, and I'll leave it for you to do, is for which one? What is left in the regular expression? The Kleene star. Now consider your R1 or R is of the form R1 star. So this is the Kleene star operation. And can you show what do we need to prove? To prove that H of L of R equal to L of H of R, right? Here R is the same as R1 star. This is what we are trying to prove, right? So this I will not do, but I'd leave it for you as a homework. Right? And essentially the important part here is that you need to show is to use the fact, the definition of R1 star. So R1 star, if you recall, the definition is, it's like the language of this, it's like the union of several such sets, L of R1 star. So let's try to recall L of R1 star. It's like L of R1 union L of R1 dot R1 union L of R1 dot R1 dot R1, right? And so on. Okay, and you also have epsilon union, right? So you have, so this is the thing. So this definition you have to use. Okay, so this is this. Now we are going to define inverse homomorphism. Okay, so given a language L, its inverse homomorphism H inverse L is X such that Hx belongs to L, right? So H inverse L is the set of those words such that X, right? Its inverse homomorphism Hx belongs to L, right? So for a string, if you consider for a string W belongs to L, we define H inverse of W for a string. It's all the set of X such that Hx equal to W, correct? And H may be from sigma star to gamma star. So W belongs to this gamma star, right? And we are doing the inverse homomorphism, right? So now, suppose I ask you two small questions, okay? I would call them just remarks. It's not difficult to see, but suppose I apply such a thing. So suppose I have such a thing, H inverse of L, and I'm considering L and H inverse of H of L. What is the relation? Are they equal, subset, superset? What do you think is the case? Maybe first you can try the second one, H inverse of H of L. So you take L, you are applying a homomorphism, and then you take the inverse. So what do you get? Sorry? So you are saying that this is same. This is what you are saying. Okay, so I claim that this is actually not equal, but this is going to be a superset. Okay, so what is the intuitive reason? You take this L, apply the H, you get all the words. Okay, so you take L, which is a subset of sigma star. So L is a subset of sigma star. You apply the H, you get something which is a subset of gamma star H of L, right? And now you apply the H inverse. So of course, every word which was there in L, if you apply the H inverse of this H of L, you are going to get that. But in addition, you can also get something more, right? So I'll just give you a small example. So suppose my sigma is the set ABC, and my L is also the same set ABC. Okay, it's a finite language. And let's say my HA equal to, and my gamma is of the form 0, 1. HA is 0, HB is 1, and H of C is 0, 1. Right? So what is H of L? What is H of L? 0, 1. H of C is 0, 1, sorry. 0, 1. Right? Is it okay? H of L, from the definition of H of L, so you take individually. So you consider the homomorphism for A, you get 0, for B, you get 1, for C, you get 0, 1. What about H inverse of H of L? What do you get? You of course get A, you of course get B, you of course get C. And what is the H inverse of W? It's the set of all these X's such that H of X is W, correct? And X here belongs to sigma star, right? So what is this? You also get AB, correct? So AB was not there in my initial set L, right? So H inverse of H of L is a superset of L. You can see. What about this one? H of H inverse of L and L? Well, I'll tell you, and you can think over this. So this is actually a subset. Why? So here, L is a, so you are talking about H inverse of L. So here, L is a subset of, first of all, gamma star, correct? And then you are applying the H inverse. Now, your H can, suppose H has, I mean, H defines from sigma star to gamma star, of course. But you can also construct this mapping just by looking at sigma to gamma star, right? You can construct, if you know this part, if you know this part of the mapping, you can construct the whole thing, correct? Because of the concatenation, the property of the concatenation. What was that? H of X dot Y equal to H of X dot H of Y. So if you only know this part, right, you can construct this whole thing. It is clear? Right. Now, what I'm saying is, it can happen that in your L, which is a subset of the sigma star, it can happen here that there are some words for which you don't have a pre-image. You may not have a pre-image, right? So then when you get, so you only get those parts, those words in sigma star for which have a mapping in the gamma star, which is a member in L. So something, so for some of the words, you may not have a pre-image, and then those things will get lost. And when you take the age back, so those things will be lost. Clear? So this is, so you can try to find out an example which will actually illustrate this. You get the intuition. It's very easy to see something, construct an example, but try it out. Okay, construct, show an example such that H of H inverse of L is a strict subset of L. Okay, and these are very simple and small homeworks, but you should try them so that you can, this thing stay in your mind and then becomes clear to you. Okay, now we'll do another thing. So we'll do closure under inverse homomorphism. Closure. Okay, so the class of regular languages is closed under inverse homomorphism. How are you going to prove this? So I'm not going to do it in detail, but I just want to hear the idea. What is the broad idea? Sorry? Closed under inverse homomorphism. Right? So you have something like an H from sigma star to gamma star. Right? Right? And then you are saying that L, which is a subset of, let's say, gamma star, and suppose this is regular L. This L is regular. What we are saying, show that H inverse L is also regular. How are you going to do this? Yeah, say what comes to your mind? Very naturally. Sorry? What comes naturally to your mind? So L is regular. So what can you do? You can consider a DFA, right? So consider a DFA A for L. Then what do you do? So consider that there is a DFA for L, and then what are you going to do? So the DFA is going to accept L by following some transitions. Now, so what is the problem that you are having? It's a pre-image, exactly. So can you get the pre-image? Is there a way to get the pre-image? Can you get the pre-image? How do you? Yeah. Multiple things can map to the same thing. So what? So suppose you have suppose you have like what you were saying, there can be multiple things which can map to the same thing. So suppose your A maps to 0, 1, B also maps to 0, 1. So you have 0, 1 here. What would you do? Sorry? So I'm just considering only that part of the H which is from sigma to gamma star, right? Because from this you can construct the whole of your sigma, the whole of the homomorphism. So it's sufficient to only kind of look at to concentrate on this part. Now what do you do? So suppose you are right that there can be multiple things which can map to this, but it's okay. I mean, you can still do that, right? I mean, you can construct a DFA, right? If you have something like this, you can have one transition on A, which is like this, and another transition on B. Often we would like it, write it like this, A comma B. But what? No, it is already, it's given here. So suppose your H is of the form, H has this. Suppose this is part of H. H of A, essentially what are we saying? H of A equal to 0, 1, and H of B is also 0, 1. Right? Now, if, correct? Yeah, it's from the definition of your H. Right? L may not have that. That's true. If L doesn't have that, then you will not also have B. So what am I doing? So the idea is that you construct the DFA A, right? Consider a DFA A for L. And the DFA A can have certain transitions. And you are going to construct another DFA, which is A prime, which is going to simulate the transitions here. Right? So suppose if you have A prime, Q prime, sigma, Q0, delta prime, F prime. Correct? And you had A, which is Q sigma Q0A, let's say, yeah. Or I can write it Q0 prime here also. Q0 delta F. And you can construct these things, right? So now I'll just write a bit of this. So what is my Q prime? What is my Q prime here? Q prime is the same as Q. And how am I going to define delta prime Q comma A here? Is the same as delta star Q comma H of A. Correct? Right? And all you need to prove that by induction again, by induction on the length of a string, that A prime accepts X if and only if A accepts H of X, right? So these are very simple constructions, right? Like, so you see, like we are sometimes, and this is even simpler. Like sometimes we might have to do changes in the state space, just like, for example, we saw when we were translating the milli machine to a mood machine, we did a change in the state space. Earlier, we looked at this odd L, right? This A L, then you had this odd of L. You had to do a change in the state space. So these constructions, like, I mean, you should have the right intuition so that making this construction become just, it's there in your, it becomes a bread and butter thing, right? Once you have the intuition, how to, we are doing all these things so that, you know, like how to come up with this construction becomes a bread and butter, right? We have to deal with these things very often. We are also going to look at these things for context-free grammars like push-down automata. We'll see that, like how you show the closure properties for those context-free grammars. We'll also have similar kind of constructions for homomorphism or inverse homomorphism and these things, right? So, and then once we have this, it will essentially, like from this previous statement, what we would get is that L of A prime is the same as H of L of A. Correct? Right? It is just like we are constructing an A, which is making an action, right? Suppose it's making a transition A such that it is simulating the sequence of transition that you will have in A prime. We are constructing an automaton, A prime, which is simulating, which is having a transition A, and this transition on A in the DFA, which is A prime, right? It is simulating a transition of H of A in the original given automaton, capital A, which accepts the language array. Clear, right? So essentially the idea is that transitions in A on A belonging to sigma, it simulates right transitions in A prime such that transitions on H of A in A prime. Clear? This is what we are transition on A prime. I'm just confusing you. A. Yes, right? So the A prime, the transitions in A prime on A simulate transitions on HA in A, capital A. Clear? Then you wouldn't have that. Sorry? You wouldn't have any transition there, correct? I mean, you can always define that, like, so for example, you go there and then there is something for which you don't have you don't have an inverse image, right? And then what you can do, if you want to construct a DFA, if you don't have the corresponding inverse image, you can just go to a trap state, right? You can do all these kind of things. Clear? But this automaton A prime is exactly going to accept the inverse homomorphism, inverse homomorphic image of the original language. Clear? So yeah, you try out a bit and try to, so I'm leaving the proof now because I think we have done similar proofs on induction several times, but if you are not convinced, then try to do the proof yourself, then it will convince you, right? Or try to do with some examples, like you'll find some examples in some book, or like I'm also giving reference to the textbooks where to study it from. So in the course homepage, if you look at the book, there may be some example that you would find, right? So try it out. So if you're given already, for example, a regular language, try to get the inverse homomorphic image of that, try to construct the automaton with this in this procedure. It can also happen, for example, like suppose there is an C and C maps to epsilon. This can also happen, right? And then what you would have, for every state, you would have a self loop on C. Clear? Right. So I think we'll just define this thing and again ask you to think about this, and we'll stop. And we are not going to show the closure properties. We'll start with this in the next lecture. So what is the definition of right quotient? Okay. So the definition of a right quotient. So suppose, let's say, let L1 and L2 be two languages on the same alphabet. On the same alphabet. Clear? Now, the right quotient of L1 with respect to L2 is, so we are going to denote it like this, is a set of X such that XY belongs to L1 for some Y in L2. So the whole string XY. So suppose you consider XY belongs to L1. So some string XY belongs to L1 such that the Y belongs to L2, right? And then you remove the Y from this XY, and then whatever is remaining, which is X, it's called the right quotient of L1 with respect to L2. Clear the definition? You consider the set of strings in L1 such that there is a suffix of that string. There is a suffix Y which is in L2. Consider those strings in L1 such that there is a suffix Y which is in L2. Okay. Right? So for example, so suppose you have L1 which is of the form an bm such that n greater than equal to 1, m greater than equal to 0, union ba, right? And L2 equal to bm such that m greater than equal to 1. So note that here this is n greater than equal to 0, here this is n greater than equal to 1. Now what is L1, L2? L1, the right quotient of L1 with respect to L2 is a set of all those words in L1 such that a suffix lies in L2, right? So you can see this is an bm such that n greater than equal to 1, n greater than equal to 1. It's a set of all such words such that there is a suffix here which is in L2. So m is greater than equal to 1. Set of all words in L1 such that there is a suffix which is in L2. Okay, just think of this. So what is the right quotient of L1 with respect to L2? It's a set of all the words which are in L1 such that a suffix of that word, sorry, we are looking without the suffix, exactly. So we are taking without the suffix. Now suppose you have something like ANBM. So suppose you have A3 B2. Okay, such a word which belongs to L1 now, and does it have a suffix which is in does it have a suffix which is in this thing? Sorry. Oh, okay. I think that's fine. Yeah. So does it have a suffix which is in L2? Yes, it has, right? So for example, for this, you can get A3 B1 and right? And so this is, of course, right? So for if you consider this word here, then this word belongs to L1 slash L2. Suppose, and this one belongs to L1 slash L2. Okay, I think I made a small mistake here. This is n greater than equal to 0. Right? And similarly, A3 also belongs to L1 slash L2 because since B2 also belongs to L2, correct? So you remove the suffix and then whatever is remaining, correct? Okay, so now you are convinced that this is the language is this, right? So now what you should think is that if L1, so this is the theorem, is closure under right quotient. If L1 and L2 are regular, then so is the quotient language, the quotient of L1 with respect to L2. Is it clear, the statement? So we are talking about closure under right quotient, right? And now whatever you have seen so far, okay, you should be able to prove this yourself. You should be able to construct in terms of automaton, like you have an automaton for L1, think of an automaton with L2, think of like, oh, you have a suffix which should be there in L2, right? And can you construct an automaton for L1, right? The right quotient of L1 with respect to L2. Can you construct such an automaton, right? And this is how you are going to prove this theorem. So think about it and we'll discuss this in the next lecture, right? So any question before we finish? Okay, so try this yourself. So we are going to meet on Thursday. Try this yourself. And whatever you have seen so far, you should be able to do it yourself. It's not too difficult. Okay. So okay, good. So I think we'll then end the meeting for today. And